In unsupervised learning and density estimation, we model data using latent variables, hidden structural factors that influence our observations but remain unmeasured. If we knew the exact states of these hidden variables, estimating our model's parameters would be a straightforward process. We would simply apply standard maximum likelihood estimation to fit the data. But because the variables are hidden, we cannot simply count them. Instead, we are forced to marginalize them out by summing the probabilities across all possible hidden states. Look at the marginalized log likelihood equation. Notice the bottleneck. A summation of latent variable probabilities sits inside a natural logarithm. This log sum structure is analytically intractable. To optimize, if you apply a derivative, the logarithm prevents it from distributing across the sum. Instead of attacking the equation directly, we construct an iterative geometric workaround, the Expectation Maximization, or EM, algorithm. We will build the EM algorithm from first principles, proving its geometric architecture guarantees monotonic convergence, and apply it to fit a mixture of Gaussians. The mathematical engine that makes the EM algorithm possible is a principle known as Jensen's inequality. To understand it, we must define a strictly concave function. Any function with a negative second derivative everywhere qualifies, meaning the standard logarithmic function fits this definition. This is a 2D graph of the concave curve f of x equals log of x. We will plot 2 points on the x-axis, a and b, and draw a straight chord connecting their corresponding outputs on the curve. If we introduce a random variable x with a 50-50 chance of landing on a or b, its expected value, e of x, sits at the midpoint on the x-axis. We project that midpoint vertically up to the curve to find the function of the expectation, f of e of x. Now we look at the y-axis. The expected value of the function's outputs, e of f of x, maps onto the middle of our straight chord. Because the function is concave, the curve always bows outward. The point on the curve sits strictly above the point on the straight chord. This visualizes Jensen's inequality for concave functions. The function of the expectation is always greater than or equal to the expectation of the function. There is exactly one condition where this inequality becomes a strict equality. If points A and B merge, the random variable becomes a constant. The chord disappears, and the two values equal one another. Identifying the specific conditions where these two values align allows us to bypass the log sum bottleneck. We return to our log likelihood equation, where the summation is trapped inside the logarithm. To begin breaking this open, we introduce an arbitrary probability distribution over our latent variables, which we label Qi of z. We apply an algebraic trick to the inside of the summation, multiplying and dividing the joint probability by our new Qi of z distribution. Because Qi is a valid probability distribution, summing over the variable z weighted by Qi is the mathematical definition of an expected value. We rewrite the inner terms as an expectation over Qi. Now we apply Jensen's inequality. Because the logarithm is a strictly concave function, we can move the log operator inside the expectation brackets. Consequently, the equal sign transforms into a greater than or equal to sign. Expanding the expectation back into a standard summation reveals a final, tractable formula. We label this new expression J of Q and theta. By mathematically pushing the logarithm inside the sum, we have successfully constructed J of Q and theta, a mathematical floor that rests strictly beneath the true log likelihood function. This coordinate system maps the exact geometric relationship between our functions. The top curve represents the true log likelihood, L of theta. The curve floating directly beneath it is our new bound, J of Q, theta. We establish our starting position on the x-axis using an initial guess for our model's parameters, which we plot here as theta sub t. The primary goal of the expectation step, the E step, is to manipulate the shape of the lower bound until it becomes perfectly tight at our current parameter guess. We want the bound to morph upward and touch the likelihood curve exactly at theta sub t. Recall the rule proven by Jensen's inequality. To force the inequality to become an equality, the variable sitting inside the function must be a constant. To make our inner fraction a constant with respect to z, we set our arbitrary Qi of z distribution directly proportional to the joint probability of x and z. Since Qi must be a valid distribution, it has to sum to 1 across all states of z. When we normalize the joint probability px, z by dividing it by the sum of all its possible values, the resulting distribution is exactly the posterior p of z given x. This mechanism defines the complete E-step. By calculating the posterior distribution of the latent variables, we mathematically guarantee the lower bound geometrically locks against the true likelihood curve at our current parameters. With the bound tightly locked in its newly calculated shape, we advance to the maximization phase, or M step, to update our parameter guess. Leaving the lower bound curve fixed in place, we simply find its absolute highest point. We mark the corresponding location on the x-axis to establish our next parameter value, theta sub t plus 1. If we project a vertical line upward from this new parameter value, we locate where it intersects our true log likelihood curve. Comparing the heights, the likelihood value at the new parameter t plus 1 rests strictly above the previous likelihood at t. This mechanism provides our mathematical guarantee. Because the true likelihood is globally constrained above the j-curve, optimizing the peak of j geometrically forces the true likelihood to increase alongside it. The E-step constructs a tight bound, and the M-step climbs it. Repeating this loop performs coordinate ascent, guaranteeing the algorithm will monotonically converge to a local optimum. We can apply this theoretical framework directly to a common density estimation problem, fitting a mixture of Gaussians to a set of unlabeled data. Consider this 2D scatterplot. We have a set of continuous, uncolored data points, and our objective is to determine the probability distributions that generated them. In this context, the E-step involves calculating the soft posterior probability, designated as W sub j sub I, that a particular Gaussian distribution is responsible for generating a particular data point. Instead of sorting the points into rigid categories, we visualize these soft assignments as mixed probabilities. Based on the current parameter guesses, a single point might be weighted as 70% blue and 30% red. During the M step, we update the means, covariances, and mixing weights of our Gaussians. We base these new parameters directly on the fractional color weights derived in the E-step. As the model updates its parameters, the actual Gaussian boundary ellipses shift their centers and stretch their dimensional shapes, optimizing their fit to encompass the highest densities of their assigned colors. This highlights the distinction between EM and algorithms like k-means, which partition data using hard binary boundaries. By retaining soft fractional probabilities, EM preserves uncertainty and mathematical nuance. Viewing the EM algorithm as a systematic variational lower bound provides a rigorous framework for optimizing complex systems rife with hidden variables.